Hello, welcome to the Blue Waters webinar series. I'm Scott Lathrop with the Blue Waters Project at the National Center for Superconvening Applications at the University of Illinois. We're pleased to have you join us today for our presentation on Pegasus Workflow Management System. Our presenter today is Matt Sering, a computer scientist from the University of Southern California School of Engineering and the Information Sciences Institute. With that, then, I'll turn it over to Mats. Welcome, and great to have you here.
Okay, well, thank you, Scott, and thank you, Francis A, for having us and hosting this series. So, as I said, we're going to talk about the Pegasus Workflow Management System, and let's start by talking about. Let me see here. Let's talk about why workflows, and I'm not going to spend a lot of time on this. Instead, I'm going to refer back to Scott Callahan's video or talk that kicked off this webinar series. He did a great job talking about the overview of workflows in general. So instead, we're going to kind of jump in directly and how Pegasus approaches these things in workflow development. So we are going to talk obviously about running computations. We're going to talk about how workflows can, or specifically Pegasus, can allow you to have a workflow that's portable. Means so we can move it between different execution environments, and how that also provides reproducibility that allows us to share our workflows, that allows other scientists to reproduce your results, and during workflow execution, how we collect provenance data. That means that, for example, where the job ran, how it did, how the performance of the job was, what environment it ran in. We're going to talk about how Pegasus handled failures and provide reliability for your workflow in general, and how we keep track of files and data in the workflow. So this is basically the most important slide, I think, of the whole presentation. So Pegasus, when I say workflow management system, the part of the system there, it's basically three components. So the first one is the what we call the planner, and sometimes the mapper, which is what takes, it makes your workflow into an executable state. The actual execution engine that we use, it comes from the HG Condor project, and it's called Dagman. And we also use Condor for scheduling and brokering our jobs. And I want to be specific here, though. Just because we use Condor for the executing and scheduling the jobs, it doesn't mean that Condor has to exist on, for example, execution environment that you're running the workflow on. Condor can remotely schedule jobs onto pretty much any common scheduler that we see in use today. Pegasus workflow are DAGs. Right? That means that they are directed as cyclic graphs. That means you're not allowed to have any cycles in the workflow. And what that means is they're not allowed to have any loops, and there's no conditional branches in the workflow. Right? So it's very simple. Here's my graph of computation that I need to do. And if the graph itself, right? If you look at the nodes in that graph, those are jobs that will execute somewhere. The edges, those are dependencies between the jobs. And most of the time, that in Pegasus, that means that there's a file that's produced by one job and consumed by another job. But it doesn't have to. You can also do explicit dependencies. For example, if you have a job accessing or modifying a remote database, and you need another job to wait for that job to finish, you can still put in a dependency between those jobs, even without having an actual file between there. Now, a very, very important kind of concept in Pegasus is that we plan the workflow ahead of execution. So that means that we're laying out the whole workflow, where the jobs are going to run and where data is going to live, where data transfers needs to happen, and everything of that is kind of pre-planned beforehand. Okay, so there are some advantages and disadvantages to this approach. The disadvantage is that if something happens during that execution, it's not like the workflow will rearrange itself. Right? We already planned it out. It's a fairly static execution plan. Um, so but it also has some advantages because we know exactly where the execution plan is. It allows us to do a lot of optimizations. And you can think about this planner as kind of a compiler in many ways. Like when you compile a code, it does optimizations. It looks at kind of the code and it tries to determine if, for example, if we can unroll loops or take shortcuts without affecting the end results. And just the same, Pegasus transforms these graphs and tries to optimize them in different ways. And we'll see a lot of examples of that as we go through this presentation. Another main concept here is that we're going from something called an abstract workflow into an executable workflow. The abstract workflow, well, it's abstract because it's missing some important details, like for example, where data is located or where software is installed. Right? So that means that the workflow is described in very general terms, and this workflow can then be planned into the different execution environments and become an executable workflow. So I have a question here, and the question is, can data stream from one node to another like a pipe? No, not currently. It's all, you produce one file in one job, and that file is then transferred possibly, but no, it's the file has to be closed, and then the job finishes, and then a job finishes and picks up the file. So there's no streaming per se here. Okay, so the abstract workflow, where was it going? Yeah, so the workflow is abstract, which allows us to be portable and move it about. And this is the way that you describe your workflow. As a user, you describe your workflow in the abstract way. And then the planning step will then fill out all the details with knowledge about the execution environment and data availability. And that executable workflow said it's important to understand that looks different depending on the execution environment that you're planning against. So if you're planning this workflow against a supercomputer or a campus cluster, it might look one way. And if you plan the same workflow against a cloud, for example, because the data management and software availability and things like that will be different, the executable workflow will also look different, right? The planner will make different decisions based on the execution environment. So in this example here, it's the same abstract workflow in the middle here, the gray area. And what we can see is that the planner has added a few jobs. There's a staging job in the top, where it pulls data in and puts it on, I guess, a shared file system in this case. It executes the workflow, and at the end we have a stage out job that takes data from that file system and puts it, in a more permanent long-term storage location. And there's also a registration job that puts the information about produced data into a data catalog. So other things that the planner might add is that's cleanup jobs. And this comes back to what I said about planning the whole workflow execution ahead of time. Because Pegasus knows where all the jobs are going to run and all the data and all the data placement, we also know the inverse of that. We know where data is not needed anymore. And because of that, we can traverse the graph and we can insert cleanup jobs at any level in the workflow based on where the files are not needed anymore. And by doing so, we can minimize the disk footprint that this workflow requires. So, and these are intermediate files, right? So for example, what we're talking about here is that there's a file that's needed here in this level and the second level here maybe. And once it has been consumed by these jobs, the data is not needed anymore, and we can insert the cleanup jobs. So we have some cleanup jobs at this level, and then we have something at the end here where after the stage out jobs, where the final outputs have already been transferred to the long-term storage, and we can then insert a cleanup job to clean up the scratch space that the workflow was using. The way that we define workflows in Pegasus is programmatically. And so we provide a very simple API. The API is available in Python, in Java, Perl, and now R. And it's really easy to use API, which basically just builds the graph structure, right? So it's you just add nodes and dependencies in there. A common question here is why don't we have a graphical editor for creating these workflows? And it's a good question, and the main reason is that our really big users have big enough workflows, maybe hundreds of thousands of tasks, which makes it not feasible to load it into a graphical editor that we have today. That doesn't mean that there might not be one in the future, or that you could do simple workflows like that. But we have chosen to just do it programmatically for now. So that API generates this XML, and that's the abstract workflow description. You could also generate that XML directly. For example, if you already have a pipeline tool that has knowledge about the workflow, you don't have to use the API and then write out the XML. You could actually do the XML directly, but that's kind of only for power users. So while that workflow is running, so we plan it, we do it programmatically, then we plan it. While the workflow is running, and we're going to go into details of these different things, but we do provide a few things. We provide a web-based interface for monitoring. We have a set of tools for debugging workflows, which I think is a really important part that people don't realize that they maybe need until once they start running workflows more. We have a RESTful API. This is something that's actively getting worked on. And Commandline Tools is what we use most, though. Pegasus has everything in Pegasus you can do with Commandline Tools, and that is kind of the main interface that we have to the system. And we're also going to show you how to pull out statistics from the provenance database. So the web-based dashboard, it's really a read-only dashboard. That means that you have to plan your workflow and submit it by hand or by command line. And once you have that, though, you can go in the web interface. You can see a list of all your workflows that you have ran in the past. You can drill down on those workflows, get statistics and breakdowns and graphs, or you can drill all the way down to individual jobs, see how they behaved and the outputs for that job. So as I said, but it's read only. It's really kind of just an informational dashboard. So the command line tools, here's a few examples that some of the command line tools we provide. Obviously, the big one is the plan command that takes the abstract workflow and goes into the executable workflow. But here are a few that's used after the workflow is done. And the top one here is called Pegasus Statistics, and it pulls out data from that provenance data that we collect, and it summarizes it. So in this case, we had a workflow that had, we can see up here, it was 100,000 tasks, 20,000 jobs, and I'm going to explain how those numbers relate to each other later. But we can see that there was some retries, there was some failures, and so we have a total number plus retries here, and it was successful. There was no failed, no incomplete jobs. The workflow wall time, that's the time that The user saw from the time they submitted a workflow until it finished. And the cumulative job wall times, these two here, are if you add up all the jobs, all the core hours that the jobs did, that this is the sum of those numbers. And the reason there's a difference between here, like was it 22 days of difference in execution time? Really, what the difference here is the data transfers, right? So the first here 1 hour, 1 year, 5 days, that's the time that your code took, and 1 year, 27 days is what if your code plus the data transfers required by the workflow. We also had some bad put. That's from those jobs that failed up there, but that's usually like this is blank if your workflow is 100% successful. Another tool that's very important, and this is not the best screenshot maybe of this tool, is called Pegasus Analyzer. And what that allows you to do is if you have a workflow that fails, you can run Analyzer on it, and it will pinpoint where it failed and how it failed. So this is, compared to grepping through logs and trying to find out which job failed. Pegasus Analyzer just drops you right in there and tells you what failed and the error, and there are even times where it could give a little bit hint of what went wrong and how you could fix it. Now, so job failure detection and handling job failures is a big part of what Pegasus does. So by default, the detection itself is just the standard, Unix convention of non-zero exit codes. If a job exits 0, it's success. Non-zero, it's failure. We do have capabilities where we can do output parsing, like you can add, you can say that if you see this in the output, that's a failure or that's a success. So we have a little bit extra detection logic if needed, but in general, it's the exit codes. The first kind of line of defense here is job retries, and that's on by default in Pegasus. So you get a few job retries, and the idea here is that maybe there was a transient failure, maybe there was a node that wasn't working, or the data transfer that failed, something like that, and giving it a retry in many times actually helps. However, there are times when the workflow exhausts the retries and have to stop. So, for example, a site that you're running against goes down for maintenance for the day. So, like, there's nothing happening for a whole day. Well, the workflow will not be able to make progress, and it will just exit and say, okay, this is as far as I can get. But what you do get from that is what we call a rescue DAG. And that means that all the work that was up until that point still gets saved, right? So when the site comes back, you can just tell Pegasus start again, and it will start from where it left off. There's no need to redo any of the computation leading up to that point, right? So that's just you start from where you left off and you keep going. And last but not least, we do have some support for checkpointing, like and this is to be specific, user user code checkpointing. If you have code that writes out checkpoint files regularly, Pegasus can pick up those files and maintain them for you, so that so if the job gets interrupted somehow, the job itself can start from the last checkpoint, and again not lose a lot of work that was done before the failure happened. Now, this is an example of output from Pegasus Kickstart. And Pegasus Kickstart is a wrapper that runs around your code, sits around your code, and this happened by default for almost all jobs. The big exception here is MPI jobs. We don't insert it by default on MPI jobs because sometimes the MPI libraries don't like to have wrappers like this. but it is possible to do it for some MPI jobs. But in general, if you have single-threaded or multi-threaded codes, this Pegasus Kickstart gets used by default. And what it does is that it collects all this information about your job. It tells us where it ran. So if we look up here somewhere, it will tell us where is it? It will tell us host names. This run at Fermilab. It will tell us things like start times, durations, U time and S times, memory used, a lot of runtime information, right? One important one is like the exit code here. So we know the exit code. We can see the argument vector that was used. We'll see down here system information. And what's missing from this slide is the environments. There's environment variables and other things that you can use later on to, well, you can use it for debugging, obviously, but you can also use it to just go back and say, what was the environment that this job ran in? And if it didn't behave as expected, that's some good information to know when you want to look back. This information is then, some of this information is then put into that provenance database, and it's then used in that Pegasus statistics tool that I showed you before. So for example, that is the duration, and the duration is the time that gets added up for the cumulative all time. A major part of Pegasus, right? And any kind of workflow system would say is data management. Like job management is one thing, data management is, I think, actually more difficult. So in Pegasus, we have three different approaches to, or three different modes, I should say, to deal with data management. So the first one here is what we call HG IO. And this is if your whole execution environment is Condor, this is a great approach. And the reason is that there's no additional credentials or anything needed because Condor does the transfers as part of using the job node authentication. So there's nothing for you as a user to do except specify files. The downside here is that the staging site is the submit host. So for small to medium workflows, maybe that's fine. Like if you're not really data intensive, pulling and pushing data from that submit node is fine. Now the second mode is called non-shared file system. And this is for, it was really developed more for like cloud computing and object stores, but it's also it can be used in the Condor mode if you want to have more control over the data management. And what's common in both of these cases is that there's no shared file system, right? So we have to do data transfers as part of the workflow management. In the non-shared file system, data is pulled and pushed from any arbitrary staging site. And the example here is, for example, if you run in Amazon, like on EC2, and you want to use S3 as your data staging site. So what that means is that when a job starts up, it has to pull the data that it needs from S3. It will put them on a local file system, do the computation, and then push the results back into the S3 object store. And it works really well with object store, but you can also do this with, for example, great FTP sites or iRods or something like that. And the last data mode is the shared file system. And this is what you use if you want to do IO directly against a shared file system. So this is campus clusters and HPC sites, Exceed. And really what happens is that Pegasus will put stuff on that shared file system. It will tell the jobs to do read and write files directly against that file system. Pegasus will track that data, but there won't be any data transfers as part of each individual job. Now, just pictures of how this works. So this is example of an HPC system. This is the the shared file system mode, right? So we have jobs flowing in from the left here. We have a compute site with compute nodes, and you can see that the data itself is just directly against the shared file system. There's I/O files getting read and written directly against the shared file system. So in this case, jobs over here and data over here are disjoint. Cloud computing is very similar, right? Except that the compute site and the object store are disjoint, but they are many times co-located, right? If you're running in, say, the same cloud, again, Amazon example, if you're running on EC2 and use S3, those are very closely located to each other. They don't have to be, though, for example. You could run outside the cloud and still use S3 or another way around. So this is just an example. But the point here is that when the job starts up, it has to use S3 pulls, puts and gets to access the data against the object store. And this example is the Condor transfer, Condor IO mode, where we'll see that both the jobs and the data is all centered around this submit node. Again, this works well for small to medium workflows, but if you have something bigger, you might want to consider one or the other data modes just to kind of separate the engine from the data management. And the other thing is you can actually co-locate this. There are Pegasus can plan a workflow against multiple sites. That's not a problem. And how it determines on where certain jobs go, it could be things like software only being available on one site and some other piece of software on the other site. So in that case, so the jobs matching the software on A will go to A and the software site will plan on B. And what Pegasus will do is it will add intersite data transfers. So it will transfer from in this case compute site A to B if data is needed on that other site. Coming back again to having this world view of where data is needed and where jobs will be running, we can be really smart of this data placement. A tool that you will not use directly, but it's kind of good to know about is Pegasus Transfer. So this is used internally, and but you will see it, like for example, if you have job workflows that are failing, you might see Pegasus Transfer complaining about transfers failing, for example. So the neat thing about Pegasus Transfer is first it supports a wide array of protocols. And what it does is, the planner says I want to transfer from source to destination, and Pegasus Transfers figure out a way to do that. Sometimes there are, we want to transfer from two incompatible protocols, and for Pegasus Transfer that's not a problem. It will break the transfer up and figure out a way of doing it. So in the example here, we want to do grid FTP to Amazon S3. Well, what we do is we pull it to a local file, and then we push it up to S3 in a second step. But the neat thing about this is that it's all done, automatically. Maybe not the most efficient way of doing it, but it's very, very convenient, and it allows you to for example, tie together data on in different locations or different places that will just come together kind of seamlessly. Some of the more parallel, or like some of the more performance oriented features here is that it does it's a threaded client. It does parallel transfers by default. It does automatic retries, checkpointing, and most importantly, it does credential management. So it knows how to handle credentials for all these different protocols. Okay, so I have a question from Slack, and the question is the submit host same as the cluster login node? So let me go back to a slide and answer that. So let's look at this case. It doesn't have to be. You can do you can have a submit host that's outside the cluster. So, for example, if we're talking about Exceed, you could have a submit host somewhere, either your institution, or, for example, we provide one as part of Exceed. There's a workflow submit host, and then you do remote job submits into the machine. So in the most extreme case there is you don't even log into these machines. You can do remote job submission all day and not ever SSH directly into one of these clusters. In reality, though, many times what you need to do is log in to kind of figure out what file systems to use and where to place data. So you might have to log in, once or twice to kind of figure that stuff out, or what allocation to charge to. But then you can just do remote job submissions, and there are different ways of doing that. A common way is still Scram, but there are other ways that, like Unicore, there are something called glidance where you kind of extend a control pool into this compute site. So there's multiple ways of doing the remote job submission. So the short answer though is submit host does not have to be the same as the cluster login node. They can be separate, and they can be the same as well. It's up to you. All right. So up until now, I've been talking about going from this abstract workflow into an executable workflow, and not told you specifically on how that abstract workflow is kind of filled out, like all the blanks in that workflow is complete. So the way that happens is Pegasus uses the abstract workflow plus 3 different catalogs to kind of find out the information that's needed. And the catalogs, there's one that's a site catalog, and that describes the execution environment. That comes back to the question on Slack about the cluster login node. The site catalog might have things like, how do I remotely submit a job to this machine? And it also has things like file systems and maybe environment variables. The second catalog that we need is the transformation catalog, and that describes software that's required by the workflow. And the third one is a replica catalog that describes what data is available at planning time. Now, the site catalog is XML as well, and I'm sorry because it's not that fun to write or maintain, but that's how it's been for a while, and there's a small effort to maybe update it to something more modern, but it's still XML. So in this case, there's a list of different sites in here. In this case, there's one that's always called local, and that's the submit host itself. So in this case, we describe 2 different directories. We have one that's Scratch and one that's long-term storage. In this case, they are file URLs. You see here is a file, so we can only access this, by directly, on mounted file system. It could also be remote file systems, right? Grid FTP or something like that, iRods. And last, there might also be things like profiles in here. In this case, there's just normal Unix environment variable that's specified. This transformation catalog, it's like I said, describes the software that's needed. And in this case, this is kind of a simple example, but it is from one of our tutorial workflows. So in this case, we need ls, the standard Unix ls. And what we're saying is that on this site, which is the Pegasus virtual machine, it's installed in bin ls. We have a little bit of architecture in OS, and type is installed. Now, if the type can also be stageable. So that is, if you have software that can easily stage to remote site. That means that it doesn't have any weird software dependencies, or it's like it's basically just a binary that you can copy over and run. In that case, Pegasus can do the software management for you and transfer it as part of the job and the data for the job. But in general, most of the time you will see this being installed. You might see some wrapper scripts being transferred with the jobs, but software itself most of the time is pre-installed. And really what that comes from is just that software stacks are getting more and more complex, right? So it used to be when Pegasus was first developed, it used to be that the approach was to make static executables and you ship them with the workflow all the time. It's less and less true over time now. You know, there's less and less support for that kind of software distribution in both kind of the tool chain. Like it's harder and harder to make static executables, and it's also the software that we see users use in the workflows are just too complex to just make that assumption. So most of the time it's installed, and the last thing, the last catalog is the Replica catalog. So what this does is it maps from something called a logical file name. It's just the file name itself, right? F.A in this case. And that logical file name, that's what we use in the abstract workflow, right? So we're saying we will have a file F.A, but I'm not specifying where it is or the path to it or anything like that. So the mapping here in the Replica catalog, though, is like if I need F.A, where can I find a copy of it? And in this case, it's on HTTP, so there's a path to it. And there's also a site variable here. The site name is sometimes it's not used a lot at all. Sometimes it's necessary. For example, if you have a local file here, like a file URL, you know, what site is that file URL valid on? Right? So the site here is important, but for at least for certain protocols. It also gives a hint to the planner to, sometimes it can optimize data placement or data transfers by knowing where the data is residing. And an extreme case of this, this is from one of our users that have multiple replicas, and what they want to do is they say, hey, we have some large inputs to our jobs, and depending on the execution environment that we're running on, sometimes the file has already been staged to the site. Sometimes the data is on some protocol and sometimes some other protocol. So we want Pegasus to try different locations in a specific order. And the order here is specified up here in pegasus.conf, right? We give it a list of different regular expressions for locations and the order that we want them to try, right? So this is a rank 1, 2, 3, 4, 5. So what we're saying is that any URL that starts with file / CVFMS, so like this specific file system, that is the one that we want to try first. Now, if that doesn't work, maybe any regular file will work. Then we'll do xrootd, which is a high-energy physics protocol. We'll do gridftp next, and if all else, just any other protocol. So in the replica catalog, what happens is that we see that the F.A, there's multiple replicas for the same logical file name. And so when Pegasus sees this, it will try these in order. And this is one of the examples of, even though the workflow is statically planned and laid out, there's still some runtime decisions being made, right? So in this case, the runtime decision is, giving this list of potential inputs, the input locations, try them in a specific order and use the one that's the first one that's found. So in this case, this CVFMS will be the first one. Then we have the local file, which was rank 2. And then we go directly to rank 4, which is gridftp. Right? So we'll try them in that order. Now, a few more features here. So I said earlier that Pegasus is really about transforming the graph. One transformation that's very common if you have a high throughput workload is task clustering. And what that means is that the task here is what you have in your abstract workflow, right? And these can be really short in certain cases. So if it's short, let's say let's say less than 10 minutes or like small number of minutes or shorter, um, the scheduler will spend a lot of time scheduling each job. And to minimize that scheduling overhead, one of the things we can do is we can say, well, take a bunch of tasks and put them into one job and run that job, on the compute site, and just one task, one after another, and then figure out afterwards what will happen. So that's what Pegasus can do. It has this task clustering can take different there's different algorithms for how to cluster the jobs. The easiest one is what we see here, which is called horizontal, where we take jobs on the same level and we cluster them together into bigger jobs. You can do, there's a vertical, there's one that's label based, which means that you can color the graph and just make any arbitrary kind of connected graph, subgraph into a clustered job. Another one, and this is one of my favorite Pegasus features, is workflow reduction or data reuse. And in this case, thinking back to the Replica catalog, so at planning time, if Pegasus can look at the workflow, look at the Replica catalog, and figure out that there are some data products that already has been generated, and it can walk the graph and remove jobs that are not necessary anymore. So an obvious reason for doing this is just saving time, right? We don't want to redo computations that we already have the data for, unnecessary computations. And this happens a lot, for example, if you have workflows that overlap. You run you run the same workflow every day that has a weeks of data. So like maybe, multiple days of that workflow has already been computed, but you're not really sure which ones. Let Pegasus figure it out and just redo the computation that's required. Another use case for this is, let's say that you run a whole workflow and then later you figure out that, yes, some of the jobs further down in the workflow didn't do exactly the right thing, and you want to redo that computation. So what you do is you just remove the data products you want to be recomputed, remove them from Replica catalog, and replan a workflow, and only the computations that you want to be redone are redone. So it's very, very, very kind of powerful feature. Another thing that is kind of more for power users, I would say, is hierarchical workflows. Any job any node in a workflow can be a sub workflow. There are two reasons for doing this. One is just scalability. You can define your workflow in smaller units and then tie them together into a bigger one. And but the second reason for doing this is kind of a workaround for the static planning problem. So there are times when you have a workflow where one job in the workflow determines the steps that needed in the next level. For example, you have a job that outputs a variable number of outputs, and you don't know how many outputs that is beforehand, but you want to run one job per output. So in that case, you can have the workflow generate outputs and then have a step in the workflow that makes a sub workflow for those variable number of files. So that's kind of it allows you to do a dynamic step into a fairly static workflow. And the key to that is that the planning of that sub workflow doesn't happen until the sub workflow is ready to run. First, at that point, that's when Pegasus will plan the sub workflow. So again, it allows us to do dynamic steps into an otherwise statically planned workflow. There's also times where we want to take a workflow that has some kind of job characteristics to run on a system that maybe is not made for that job type. So in this case here, we have a fine-grained workflow, a high-throughput workload, and we want to run it on a more traditional HPC system that prefers, larger MPI jobs. So, and the reasons here are many, right? First, you don't want to flood the queue with like small, tiny little jobs, and an HPC system might even have priorities based on job size. So, inserting like smaller jobs into the queue of this is not beneficial. The HPC system might also have limits on how many jobs you can have in the queue. So we need to package up the workflow somehow. And in this case, we use a tool called Pegasus MPI Cluster, and it is a derivative of the regular job clustering, where we can color the workflow, we can color the whole workflow, or we can color a subgraph and say, hey, this graph here, run it as one MPI job on this remote system. So this is again really useful when you want to run on one of the bigger machines and you have a workload that's as high throughput. Your applications themselves are not MPI in this case, right? It's just they get run on the system in kind of a master worker MPI container. So it's just taking part of the sub workflow, running it as a remote execution as an MPI job. Again, it doesn't mean that there's MPI communication between your tasks. It's just that the MPI communication is all about scheduling your tasks onto the nodes that are assigned to this MPI job. Now, another feature that is internal, but it's good to know about, there's support for metadata. And this is at different levels. We can assign this to either the workflow level. So in this case here, this is abstract workflow, right? Like the XML abstract workflow, and we have the metadata here for at the workflow level. This is some kind of experiment identifier. Down here we have it per job, where we can give a little bit more information about the job. So again, when we look back later on how this workflow ran, and we can look at the details here about this about the specific job. And then last level is we have it per also per file level, where we can look at saying we can tag some extra metadata onto the files that can be helpful later. And most of the stuff you're seeing here is static metadata. There is also some dynamic one like file sizes that gets added. There's some checksums and things like that's kind of dynamically generated as the workflow is executing and added into the metadata catalog. So reviewing now what the planner does, going from the abstract to the executable workflow. So starting from the left, we have the abstract workflow. And the first algorithm that gets applied is the data reuse. That's the reduction that we talked about, where data exists, that there are some nodes in that abstract workflow that we don't even have to redo anymore. So we can clean that up and make it smaller. We have a site selection step where we decide where the jobs are going to run. We do task clustering. We do refiner, where we can again look at where data is available, and then add directory creation and file cleanup nodes. If it's Pegasus MPI cluster, we have to add a remote workflow engine node in there. And then we have an executable workflow that gets generated on the file system. Now, I have a few examples of some of our users, and they are not super detailed, but I still want to kind of give you an idea of how Pegasus is used and the scale that it's used to. So the first example here is LIGO, and obviously we're very proud of being part of a project like this, and with the successes they've had last year detecting the gravitational waves. But LIGO has also been a long-term collaboration of Pegasus and also a driver of some of the features. So Pegasus, LIGO is using the data reduction or reuse algorithm a lot. It's been a driver for some of the replica selection. They are the example that I talked about before, where they can have data in multiple locations based on the execution environment. So it's been great working with LIGO just to get that kind of driver for these features. The workflows themselves are large and complex. If you look down here, for example, that like this last bullet here is for the validation run that they did after the detection. Excuse me. And you see it's like on the order of 200,000 jobs, 20 million core hours. So these are some pretty big high throughput workloads. And you can also see here, like in the insert here, like there's some stats. This is not complete, but you see this order of 20,000 workflows, maybe a year, I think, and over 100 million tasks. So these are really good sized workflows. Another example I want to show is some work I did with a user running an XSEC last year. And this is a pretty standard DNA sequencing pipeline. But what I find interesting about this example is that the data management here is that the data lives in this data store. It's called iPlant. On the iPlant, they changed the name now, Cyverse. So Cyverse keeps this this data for the project, and when the workflow starts up, it transfers the data, and this is terabytes of data from Cyverse into XSEC. We do the computation of XSEC, and then we push the data back up into that Cyverse, and that allows us to do downstream analysis on the data. So the user run the workflow, then they can log in and they can graphically analyze their data with the Cyverse tools. As I said, it's a pretty standard sequencing pipeline. The normal tools and stuff that are used. But one of the problems running workflows like this is, if you look up here in the right corner, you see that there's a list of different tools, and they have all different requirements. They have different number of cores. So these are multi-threaded codes. Some of them are multi-threaded algorithms, and they have weird memory requirements. And these are all application specific, not only application specific, but they are specific to this use case, right? So if you ran these tools with a different data set, you might get different memory requirements. But in this case, these are the requirements that the product came up with. So this put some challenges into the workflow engine to be able to schedule these efficiently. It used to be that this workflow ran with Pegasus MPI Cluster on TAC Stampede, but it has since moved over to TAC Wrangler for two reasons. One is the really awesome Flash-based data file system that Wrangler has. It allows us to really good I/O, and the second thing is that we have higher memory per core ratio here, so it makes it easier to schedule these large memory jobs. But what I also want to show you is this graph here in the lower right corner, which shows the same workflow running with and without cleanup. So this is a small version of this workflow. A real workflow is probably about 10 times this. But even for the small version, you see that the footprint here, this axis here is terabytes, so it's 3 terabytes up here. And if we don't run it with any cleanup, that's a red graph, we'll see the ever-increasing disk footprint going up, all the way to 3 terabytes. With cleanup, though, we still have a big spike here in the beginning, and this is basically a data reduction workflow, so that's expected. And then we see all the drops here. That's the data cleanup algorithm kicking in and removing data that's no longer needed and minimizing the footprint here, right? So it's a good example of why, when the cleanup algorithm can make a big difference. Now, the last example I have is Southern California Earthquake Center's CyberShake workflow. And if you want details about this workflow, again, urge you to go back and watch the first video of this webinar with Scott Callahan. Scott Callahan is the author of this workflow and the developer and the person that runs it. So he has more detail than I have, and he probably even has a newer version of this. This slide I have is old, but it's almost a little bit on purpose. And the reason is that this workflow, it's first a hierarchical workflow. So this up here is the top level workflow, and these are sub workflows, right? So there's two levels. There's one here, here's the second level, and third level on here. And the reason I like this workflow, talk about this workflow, is that it is a mix of MPI jobs and high throughput jobs. So it used to be that this workflow, we used to plan it on different, like it used to be multiple sites. So like this first part here with the yellow jobs specifically being big, large MPI jobs, they were planned on, I think Exceed, or could even be Tergrid at that point, but they were planned on the more traditional supercomputers. And then what happened was that the Pegasus did into site transfers, and it ran all these high throughput parts on things like Open Science Grid or other high throughput execution environments. And that is not really fully true anymore. Most of the time this is done, like the jobs here in this sub workflows have changed over time, and they're a bit more parallel than they used to be. So this workflow nowadays mostly run directly on the larger systems, Blue Waters being one, and it's a very kind of well optimized workflow at this point, but it's also a really large one. They do campaign modes where they run these workflows for a few months and then get new data set, and then they spend the rest of the year and do an analysis on that. So almost my last slide here. Upcoming features. So I want to mention a few things that we're kind of excited about. So currently what's being worked on is version 4.8. The current release that we have out is 4.7.4, I think. So 4.8 is the next release, and is coming out here in the late summer. And there's two kind of main focuses on it. One is containers, native support for containers. Pegasus can run on top of containers now, and that's not a problem. But what we're talking about is adding more native support where jobs can pull in containers dynamically, and we can manage the image as part of the workflow. There's also some Jupyter Hub work going on. This is something that's going to be great for developing and demoing and training, where you can run workflows directly from Jupyter Hub. The question is a little bit how big the workflows can be, right? Like, is there a limit to how long you want to wait for results? But as I said, for certain use cases, that's going to be a really nice thing to have. And 4.9, which is, there's no real date for it, but it's probably early 2018. And a big focus of that is data integrity. And the idea is that we're going to extend Pegasus to do even more data integrity checks, and it's going to collect more data integrity metadata, and it's going to do validation in different parts of the workflow, basically just increasing the confidence in the results that you have, that there hasn't been any, it could be malicious, but also like just any undetected transfer errors or data sitting on a file system and maybe being corrupt. So we want to be just increase the confidence in those computations by doing an additional layer of data integrity. So that's my last slide. I just want to leave you here with a few pointers on where to go if you want to have more information and if you want to play around. So the first thing is the Pegasus website, which is pegasus.isi.edu. I'm going to show you quickly after here just a few features of the website that you might find interesting. Another thing is that you should know about is there's a user mailing list, Pegasus users at isi.edu, and you know, that's for general discussion. There's a support list for Pegasus support at isi.edu, which just goes to developers. And we also have a HipChat window that if you go to the website, you could start to chat with us. I'm not promising that that's always manned, but if we are around and we see somebody ask questions, yeah, you know, that could be a really quick turnaround on questions. So I also have another question on Slack, and the question is, must Pegasus replace the existing resource management system, for example, Slurm? No. We will use Slurm or whatever system you have. Pegasus will schedule jobs into Slurm, right? And the way it can do that, there's there's multiple ways, but one way is remote job submission, like GlobusGram, for example, where we just use one of the APIs to to give jobs to Slurm. Another one is if you're co-located, you can have Quandra directly do Slurm submits. This is something that we use a lot on our campus cluster here at UC, where our scheduler is PBS, and so we have a submit node where the Condor, like where Pegasus puts jobs into the Condor queue, and they then translate into PBS jobs automatically. So we just leveraging whatever scheduler is already on the system. And the third way that we can do is what we call glide-ins, where Condor puts it submits a job to Slurm, but that job is just a Condor kind of compute daemon that can then pull in jobs. And this is like the old pilot job model that, if you listen, for example, to Shantanu a couple of weeks ago, talked a lot about pilot jobs. So that's a really good way of doing it if you have a high throughput workload, because you can reuse that slot over and over again and kind of get a better throughput by doing so. Okay, so before just quitting here, I'm going to just show you the website a little bit quick, because I want to point out a few things. All right, so again, the website is Pegasus, that I said edu. And so one of the things we didn't get to here today, but is kind of interesting. So first, under documentation, under user guide, we have a tutorial. Right? The tutorial here is self-guided. It is virtual machine based, so you can download a virtual machine and you can just go through the tutorial by hand. So that's good to know about. And obviously, the user guide has all this other information about execution environments, data management, and all this stuff. Now, the other thing I want to that's kind of fun is there's an application showcase that shows some of the applications that are currently using Pegasus. These are not very detailed. It gives you a little bit of overview and a little bit of maybe the workflow data structure, but it's interesting to see, you know, the applications that are out there. And the last thing I want to show you is so Pegasus being, you know, it's mostly there's two aspects to Pegasus. One is the product, the engineered product that you know it's available for download and use. There's also kind of the workflow research side, and if that's what's interesting you, you can go to research publications, and you will get a list of our publications, and also you will find a list of all the presentations. So if you want to see slides, for example, from today, here's the slides for today. You can go here and find them. All right. So I have another question. Let me go back to the website here. So show that. So the question is, would Pegasus use any resource on the login node other than, say, SSH? Well, it depends. So In general, we don't run anything on the login nodes, right? Like that, so the short answer is no, where we would say whatever remote job interface or data transfer interface that you provide, we will use those services and those services only. You can always change how that workflow is mapped to the remote site though. So for example, you could say that I want my data transfers to happen in a login node. And that is common if you have a cluster that sits on a private network and you don't have any outbound network connectivity. You might not have a choice to use anything but your login node. But we do try to prevent that. Uh, we really try to play nice with these resources, and we understand what the policies that the site owners have. So we really try our best to play that. All right. So another question is there web interface for Pegasus workflow creation? No, there's not. We have actually had them in the past. There has been people that been playing with the idea and have had them, but no, not really. It's API driven, and that's what the main way of constructing a workflow is. All right, another question. You have mentioned that Pegasus could pull data from multiple resources. Is it possible to target multiple clusters in a workflow? For example, send 40% job to exceed and send 60% to local cluster. Yes, so that goes back to, well, I had it a little bit on one slide. Let's see if I can find that slide again here. This one here. View. Let's see, does that work maybe? Yeah, okay. So in this case, the workflow is planned to multiple compute sites. The question is a little bit of how do we decide where to run a job, and there's multiple reasons to make the decision. So in one case is you don't have a choice. For example, if you only have software available on one site, the job has no other way to do it than to run on that site. You can also in your abstract or in somewhere in the site catalog or somewhere specifically say, I want this job to go to this site, so you can make it. And if it comes down to, hey, the job could run on either site and it doesn't matter, the planner can just randomly pick one. So there's different ways of kind of making the determination of where the job runs. But if you have multiple sites, they're like the planner will try to be smart about it. If there's no if it's just too if it's not specific enough, then then will be random. Okay, so any other questions? I guess I have to wait for a few seconds, right?
Yeah, let's give people a couple seconds to post their questions. And while we're waiting, maybe I'll just ask a general question after a really good presentation. Thank you. When people are starting up, is there any obvious gotchas that you would warn people to watch for them when they're first getting started?
No, well, there probably are. I just don't know them. I would recommend doing the tutorial. That will give you a feel for these Commandline tools and how to do the abstract workflow. Part of that tutorial, there's a Pegasus init command. So if we go down to, again, user guide here, and we go to the tutorial and then submitting an example workflow, one of the things you will see is Pegasus init command. And the idea here is that this will give you a sample workflow to get started with. And the idea here being that, myself and a lot of developers, we like to see examples and we like to have something starting from and not just start from scratch. So Pegasus init gives you sample workflows that can be used in the tutorial, but they can also be used to kind of, here's a starting point for your own workflow and then get started. And the last thing I want to mention is that there are we did an exceed tutorial. I should have put a link to this, but if you Google for XCEC workflow tutorial, it will be a Google site here, workflow systems on XCEC. And what this does, it does have the different workflow systems. Some of them we'll be talking about, and it does have an XCEC tutorial. So this will show you a little bit on how to run a workflow in a more maybe production ready way than what the tutorial VM will provide. Okay.
Fantastic. Well, thank you, Mats. This was a fabulous presentation. I really appreciate it. And on behalf of everyone here, thank you very much.
Thank you. And yeah, again, I appreciate LCSA hosting this and putting this webinar together. It's been great watching all the other systems and you know, interact with the users. Thank you.
Thank you. And if we'll bring up our final slide. Again, if people have questions, feel free to go ahead and post them, and I'm sure Mats will be available to help answer any questions you may have after this. So thank you, Mats. It was great. There is no webinar next week. The next two webinars, the first on visualization would be Wednesday, June 7th by Mark Van Moor on visualizing non-spatial data. And the next workflow webinar will be Wednesday, June 14th by Peter Kaysen on Copernicus. We do have a very short 5-question survey. Those of you that are watching live or watching the recording, we encourage you to fill it out, both to let our presenter know your feedback and to help us improve future webinars. With that, we thank you all and take care. Bye-bye. Thanks again, Mats.
Thanks and bye.